All right, so remember how we had enantiomers that were conformations of each other? You rotate their bonds and they can become each other. Well, now we're going to look at diastereomers. Diastereomers. There we go. Diastereomers. While enantiomers were conformations, diastereomers are configurations, which basically means they need to break bonds to become one another. So two molecules, they don't rotate their bonds to become each other. They break them. So as you see, they really are their own ride or die stereomers. It is 1:04 a.m. on a Friday night or early Saturday morning. And I am in my room making chem videos for all of you. All right, back to the video and what's actually important here. So diastereomers, they have two types. They have either cis or trans. All right, no R and S. R and S is for conformations. Okay, enantiomers, conformations, R and S. Diastereomers, configurations, breaking bonds, cis or trans. And basically, go ahead and just show you guys what cis and trans look like. Cis just means that our main atoms are on the same side. Wow, what the fuck are main atoms, huh? Well, show you guys in just a moment. Got two conformations here for this molecule. Cis and then the trans. Before you guys go like, oh wait, but the chlorines, they're on different sides on the cis. You said cis was the same and trans, they're on the same side here too. Yeah, well, the main atoms are the ones that are on the same side. And what are the main atoms? They're the heaviest ones. Remember how CIP looked at the heaviest atoms? Well, cis and trans also does. You pretty much use CIP rules for almost everything. So on this side, heaviest atoms is the Br. On this side, the heaviest atom is a Cl. The heaviest atoms, the priorities, the main guys, big ones, absolute units. Same side, cis. Over here, trans. Got it one here, on here, right? So make it a bit bigger. Opposite sides, right? Main atoms, heaviest one is Cl, heaviest one is Br. Main atoms, different sides, they are trans. All right? Man, I wish that were me right now. I'm trying to make a chemistry video. Okay. Anyways, let's just all right, just stop the recording real quick. I think they're gone now, so I just waited it out. Okay, diastereomers, right? Cis and trans. Let's go ahead and look at an example of how this works IRL, you know. So say we've got a molecule here. 1, 2, 3, 4, 5, 6. Victoria. Let's make this a phenol ring. Right. Methyl group here. Another methyl group here. All right. What is this? Is this cis, trans? What is it? Well, let's take a look. First of all, we gotta find our two chiral centers. Remember what chiral centers are? Well, I hope you do because I do not actually do. Okay. Chiral centers is when you got an atom attached to 4 different stuff. Okay? 4 different ones. So let's go along this chain. That's 3 hydrogens, right? This is a methyl group. This is attached to 2 hydrogens, and we keep going and we find out this right here is our chiral center. And yeah, I'm gonna spoil it. This one's also a chiral center. But wait, this is attached to carbon and this is also carbon. What's going on? Well, guess what? This carbon is different. It's attached to a methyl like that. This one attached to 2. They are different. Well, it's attached to 3, so you see them. They are different. They are different. That is my point. And in diastereoisomers, when you're labeling these cis and trans, oh, I almost forgot. I'm so sorry. This has a double bond. Oh, well, at least you learned how to label them without having to use a double bond as a reference. Typically, when you label cis and trans, from what I've noticed, is that you can use where the double bond is as your reference point, and the 2 carbons are attached to them. That's just where your 2 carbons are to determine if they're cis or trans. So let's go. Have our chiral center right here, and now what we do is we find the heaviest atom that is attached to that chiral center. Got a carbon here. All right, got another carbon here. Got another carbon here. They're all carbons. Timed. Oh, and we got. No, we don't have hydrogen. My bad. Okay. Now, what do we do? Well, we go ahead and we see what each of these are attached to. This carbon here is attached to a hydrogen. Oh, and notice how I'm not counting this one twice in this case, huh? Well, because if I did count this one as twice, then I mean, I don't know, I guess it's something you just don't do. In the examples I went through, I didn't really count the double bonds as twice. Maybe because, oh, I don't know, it's an axial chirality case here. This is a chiral axis, not a chiral point. Yes, yeah, okay, we have our chiral centers here, but because we've kind of got 2 chiral centers and a double bond connecting them, we've got axial chirality. All right, so that's how we're not going to count that carbon twice. All right, this one is attached to 3 hydrogens, and this carbon here, hydrogen, hydrogen, bam, carbon. Carbon is heavier than hydrogen. All of these guys are canceled. And that means that we take our red and we connect this to the heaviest one. Ooh, connected. Same process on this side. Carbon here, attached to 2 other carbons. Carbon here, attached to another carbon and some hydrogens. So let's go ahead and write it down. It's carbon, carbon, carbon. This one here is attached to hydrogen, hydrogen, carbon. Now this dude here, so it's pretty interesting. What do we have? Oh wait, my bad, almost forgot. Gotta remove a carbon here because actual chirality, it's only attached to 2 others. My bad. Let's look at this guy now. This center right here is attached to 1 carbon here and double bonded to a carbon over here. Now, because this double bond here is not our axial chirality, whatever, it's not this guy, right? It's not that guy. We can count it as twice. Okay, well, this guy's got the most carbons. It's got the most heavy atoms. So this thing right here is going to be our main guy, main group, right? Take our red, move it up, two main groups. They are facing each other, and this is cis. Bam, there we go. Let's look at another example, which spoilers will be trans, but at least you guys get to see how it's done. All right, so let's go ahead and start with a phenol ring. 1, 2. There's our double bond. Where's our chiral center? Well, it's right here. Two ends of this double bond. Double bonds are usually a sign that you're going to have a diastereomer, because usually I feel like you only see them in diastereomers. I don't know. When I was doing the enantiomers, I didn't really see them on any of the example problems. So we're just gonna go with that one. Anyway, as always, I have no, oh, my water bottle, ouch. Okay. As always, I have no teaching license, credential, or any of that. So let's just go with it. All right. So looking at our heaviest atoms right here. Let's look at this guy. But what's this guy connected to? Well, yeah, it's connected to carbon there, but we're just gonna kind of ignore it. It's connected to a carbon here. Oh wait, I forgot. It's not a carbon. If it's an oxygen here. Yeah. Sorry, I got the molecule wrong. All right. Okay, well now you know which one's the heaviest. Okay, this is a carbon. This is an oxygen. It's gonna be the oxygen, right? That's gonna be heaviest. So let's go ahead, take our red marker, draw a line to it. This dude right here, you've got another hydrogen over here attached to it in the methyl group. That's just fancy for carbon and 3 hydrogens attached. Okay, yeah, obviously the carbon's gonna be the big one. Bam. Two groups, 1, 2. They are facing opposite ways. This is trans. Nice. All right. So that's pretty much the difference between cis and trans when it comes to diastereoisomers. And just a quick thing about these is oh yeah, diastereoisomers don't really have chiral centers, but or no, they don't really exhibit chirality. Yeah, okay, makes sense. All right. One last thing about this no double bond here. I know I've been referring it to be like a chiral axis of sorts, but I mean I'm not sure what else to refer to it as. So comment below if you know what I should refer to this double bond as. I feel like it should be called a chiral center. But either way, the process still the same idea. You find what this guy is attached to outside of this bond. So this bond, just don't think about it when you seeing what this guy is attached to and finding your heavy atom, okay? Just look the other way. Look the other way and see what it's attached to. Same thing for this guy. Look the other way and see what it's attached to. All right. Important point. Alkenes. So these guys, right? They're not chiral in this case, at least. And this is because apparently they are flat, and anything that is flat has a mirror plane and is not chiral. This is straight from the lecture. I'm not too sure what it means, but just to put it out there, alkenes apparently are not chiral. So I'm guessing this is alkenes, like they're not chiral to each other, not like within the molecule, but like two alkenes will not be chiral to each other. And I guess, yeah, I guess that does make sense in some cases. Anyways, that's beyond the point. So back to diastereomers. All right, so diastereomers, once more, formal definition, they are non-mirror images of each other, right? They have their cis and trans, and they are non-superimposable. They do not match up, okay? Do not match up. Non-superimposable, non-mirror images. And as we've seen thus far, diastereomers are different configurations. They can have cis and they can have trans, okay? And very important is that the diastereomers have 2 or more stereogenic elements that are present in the same molecule. Okay, so in other words, they have 2 or more chiral centers. We saw that earlier with this thing, right? One center here, one center there. Okay, and to determine how many, I guess, stereoisomers there are of a certain element, you can just go ahead and do 2 to the power of n. So if your molecule has 2 chiral centers, you're going to have 2 to the power of 2 stereoisomers in total. Okay, so chiral centers equals 2. The number of stereoisomers, 2 to the power of 2 is 4. Let's say that now it's 3. 2 to the power of 3, it's I think it's 8. So you're gonna have 8. All right. Okay. However, it is important to note that in real life, you're going to actually have less than 2 to the power of n stereoisomers. And this is where we introduce meso compounds. Okay, so meso compounds are a type of diastereoisomers, okay, type of diastereoisomers, and they are achiral. This is usually due to improper rotation axis. Improper rotation axis is just fancy for weird axes. So like maybe you'll have one like this or one like that. Maybe take a geometry class. All right, this is chemistry, not geometry. Okay, so they have a plane of symmetry and they are not chiral. Okay, so let's take a look at an example. Yeah, this seems really complex, but we're going to boil this down to something real simple. Okay, so let's say we've got our compound here. And we're not gonna use chemicals. We're gonna use colors again. All right. Okay. Actually, you know it's an even simpler way of doing this? Just go ahead and do. And we're gonna use colors again. Got two molecules here, and they've both got some red attached to them. And what's really cool is that these 2 molecules, they're actually meso isomers of each other. How do I know? Well, let's remember the definition. Meso isomers have some sort of symmetry in them. That's the biggest giveaway. They've got a symmetry. Here, or a symmetrical plane at least, they've got some symmetry going on. Got kind of a symmetrical plane. They're reflecting. Both of them are actually. They're symmetrical. Check. They are symmetrical. Another thing is that they are not chiral to each other. These 2 guys are absolutely not chiral to each other. How do I know? Well, they're not mirror images. Just look at them. This guy's got this wedge here, This guy's got two, I guess, shaded wedges. This one's got two dashed wedges. They're not mirror images. They just aren't, which means that they're not chiral. And that's usually the easiest way to find the meso compound. Check for symmetry, check if they're mirror images of each other. If they are, if that is the case, then guess what? They're meso. Let's find another, maybe make another example. Maybe this time let's use some chemistry. So we've got a 1, 2, 1, 2, 3, 4, right? Oh, that was a pretty great example. Got this compound here. I'm going to make the other one. All right. So what do we have here? Well, let's look at them. In fact, let's draw in some, let's draw some colors to make this one easier on us. Draw some colors. All right. So first things first, plane of symmetry. Bam. This is symmetrical. Got that one down our list. For our meso checklist, we got this. Symmetry plane. This one here. Bam. Symmetrical. Got that one down. And now our next one, are they chiral? So let's check if they're mirror images. These two here, they're not mirror images, and let me tell you why. This is a shaded wedge. This is a dashed wedge. Yeah, if this one was shaded like this, then yeah, they would be mirror images. Congrats. But guess what? They're not. They're not mirror images, which means they're meso. Right? Symmetrical and achiral, they are meso. Now, a final thing that we're going to do here is kind of go ahead and try and bring everything together. All right? Okay. Maybe for a bit, keep the meso. Maybe just keep it to the side for a bit. But yeah. We're just gonna go ahead and bring everything together. We're gonna bring our diastereomers and the enantiomers together. All right, so remember when I said that RNS is only for enantiomers? Well, you see, I kind of lied about that. They can be used for diastereomers as well, but in kind of a different way. Well, okay, every chiral center can have R and S assigned to it, but only diastereomers will have E and Z or cis and trans assigned to them. So maybe take a screenshot. All chiral centers have RS. Okay. all of them. Only diastereomers, you know what that says, have cis trans. Okay? Take a screenshot. Remember that. Now we're gonna see, well, what the fuck is going on? Now diastereomers gonna have RNS too. Jesus, okay. All right. RNS in this case is actually really helpful to kind of show the relationship between some molecules. So what we're going to do is we're going to make up a molecule. This molecule is circle, this one is square, this one is triangle, and this one is X. And they all have, well, they've all got different stereochemistry. They've all got different R and S configurations. So usually this relationship between like diastereomers and enantiomers, they really only work if you got two or more chiral centers. So before we go into this example, what I mean is the stuff we were seeing earlier, where you've got like stuff like this. We've got two centers right here, two chiral centers. Because when you have two chiral centers, you can name them as like, oh, this is R and this is R. Or you can maybe say that they're SS. Or maybe they're a combination. R and S, or S and R, and so on and so forth. And that's really kind of what allows us to have this like relationship between diastereomers and enantiomers and so on and so forth. So let me show you what this is. And don't worry, we're gonna recap everything at the end. It'll make sense, I promise. So let's say that this one has R comma R. Okay. It's got both of its chiral centers have R. This dude, both of its chiral centers are S. This one is R, the other is S. And for this one is S, the other is R. No, they're not interchangeable. What is this? Well, if their stereochemistry are opposites, like R and S, they are opposites. They are enantiomers. Okay? R is the opposite of S. R is the opposite of S. They're enantiomers. If only one of them is the opposite, R is the same as R, but R is the opposite of S, and guess what? Yeah, they're diastereomers. Let's label that with D. SS, same thing, but S is the opposite of R, diastereomers. And you can also do it cross this way too. They will also be diastereomers. All right, so opposite of these, opposite stereochemistry, these two, enantiomers. One is the same and the other is opposite, like these two, diastereomers. All right. So let's go ahead and scroll through where I wrote some. Okay, pretty good stuff. All right. So this all comes down to the final question. How do I determine if something is an enantiomer, a diastereomer, or a meso compound? Well, there's some steps you can take, and they're not that tedious, hopefully, not the hardest things ever. So let's begin. How to know it's an enantiomer, diastereomer, a meso compound, Maybe even if they're the same molecule, but if they're the same molecule, you'll probably be able to tell. Okay. First step is to check connectivity. All right, check how the molecule is connected. If they're connected in the same way like these two, congrats, you can move on to step 2. However, if they're connected differently, like these two, not too bad. You stay at step 1. And guess what? You've just done constitutional isomers. So different connectivity means that you have constitutional isomers. Okay. Step 2. You just learned that you don't have constitutional isomers. Well, now you need to check R and S using your CIP rules. All right. If they're all opposites, like RR, right? Remember RR, SS, all opposites like that, you've got enantiomers. If only one of them is the opposite and one of them is the same, you've got diastereomers. So same or and opposite, you got diastereomers. Okay, so if you got like R comma S and then R comma R, they're diastereomers. And from these diastereomers, you can go ahead and decide if it's cis or trans. Remember, because enantiomers don't have cis or trans. Diastereomers have it all. Enantiomers, they've just got R or S. If, however, they are all the same, you have something that's RR, and the other one is also RR, then you've got the same molecule. So everything is same. You've just got duped. That is the same molecule. All right. You checked your RNS. Everything is great, but you've got to do one more check just in case. And that is check if you have a meso compound. Remember that meso is a type of diastereomer, essentially. So if you got a diastereomer, then you can check if it's meso. So only move on to step 3 if you got a diastereomer. In step 3, we just check for symmetry. Why? Well, okay, we know that diastereomers are non-chiral. So we already got rid of the non-chiral, I guess, requirement, right? We're already past that. Now we just need to check for symmetry. And remember that this usually only happens when we have 2 or more chiral centers. Okay, same thing as diastereomers also usually happen when we have 2 or more chiral centers. But if there is symmetry, then we've got a meso compound, right? That's how we know we've got a meso compound. Okay. So I'm going to leave this here. Go ahead, take your photos. If you've got any questions about any of this, feel free to fill out a question form. Check the website. I think it should be posted there. As always, feel free to subscribe. Also, if you want notifications, turn those on so you know I posted some more trash. And yeah, all right. Awkward goodbyes. Where is the stop recording?